Hi guys. So I guess tech event sometimes also means technical problems, but now we are ready to start. For those who haven't met me, my name is Nadiya Shvai. I am a senior data scientist at Cyclope.ai, and I'm also a research manager. This is kind of a second type of the hat that I carry, but today I'm going to be in my first role, so senior data scientist. And my task today is present one of the projects that we have been working on for 5 years now. So it's in a quite mature state. It's about incident detection in the tunnel. So we're going to be talking about the road safety. Perfect. Okay, so the talk is going to be like this. I'm going to say a couple of words about the company where I work, Cyclope.ai. We're going to characterize the problem. What is the incident detection in the tunnel? What kind of situation do we want to detect? And what are the constraints there? We're going to present the solution and conclude with some perspectives. Okay. First, Cyclope.ai. It's a French software development entity that specializes in the artificial intelligence solutions for the image processing and video analysis. We have been created in the end of the 2017 by the Vinci Autoroute, which is a large concession company in France with over a couple of 100,000 people working for it. And here you see a range of the products that we have developed over these 5 years and that we have been continuing to improve. So first is the Tunnel Watch. It's a commercial name for the automatic incident detection in the tunnels. And this is going to be the topic of today. Second one is a toll sense. So this is the vehicle classification at the toll, and historically is the first product that we have developed and deployed. So we started with a small team of 5 people. And when we just deployed it, we had like this small counter in the office to count the amount of vehicles that we have classified at the toll. And it had, I think, 6 digits. After some time, we ran out of the space to show the amount of cars that we have classified. And now we classify over 1 million of cars every day in France. Next one is accounting. It's actually a range of the projects for the analysis of the traffic to understand how many vehicles pass on the road, which lane, what type of the vehicles, how many people in the front seat. Are the cars properly using the dedicated lane for the public transport, and so on and so forth. So it's much simpler than Tunnel Watch, for example, but simple isn't bad, it's actually good. It's one of the highly requested products that we have. And finally, the carpooling. So kind of a hot topic, particularly in France. It's about smart usage of the infrastructure, having a dedicated lanes only for the carpooling, and then monitoring that they're correctly used. So, okay. Now we're going to be talking particularly about the incident detection in the tunnels, and I'm going to start with the motivation, right? Why do we want to do it properly, and why there is strict regulation, particularly in France? I think quite a few of you heard about the major incident in the Mont Blanc tunnel that happened in 1999. There has been fire that lasted for 3 days, so particularly 53 hours. It caused major death incident of the 39 people and destruction of multiple vehicles. After this, the tunnel has been closed for the 3 years. And the following trial showed that the main reason why this was possible is that the emergency procedures were not followed correctly. This has caused to the restriction of the safety measures in France when it concerns the safety in the tunnels. And our company have developed a product which helps to automate the incident detection. So first, I'm going to be talking about what kind of incidents do we want to detect and the constraints, right? So first main constraint, even before I go to the types, is the real time. And not just the real time, I want to be detecting them really, really quickly, right? So for example, for the runway vehicles, I want to detect them in under 5 seconds. And it's not only the data science part, right? So there are other parts in this pipeline. It means for the data science, I need to do it really, really quickly, like 1-2 seconds. Similar for the other type of the incidents. So what are those? Typically, they concern vehicles, rather abnormal behavior of the vehicles, such as stopped, going wrong way, being slow, then a combined behavior of the vehicles, congestion, particular agents that shouldn't be there in the tunnel is the pedestrian, and the kind of the obstacle object that might appear in the tunnel. And finally, a bit of a standalone incident, it's the smoke. Like final constraint is the amount of the false alarm that we are allowed to have per camera per day. So you see here numbers like per camera per specific amount of days, and as an additional constraint, at the most 16 false alarm per tunnel per day. So in this particular case, like this is the first ever DAI product that we have developed, where DAI stands for the automatic instant detection. Just the acronym is in French, that's why the order of letters is different. So here particularly we're talking about 96 cameras. Tunnel is 96 cameras. Okay, so the incident videos are usually either like not very interesting or not very pleasant to watch it, but I have found you a nice one. So like what do we see here? We see here a stopped car, 2 pedestrians, then the car going slow, stopping, then again going slow. So normally we should be able to detect all of this and quite fast. Now let's try to design a solution based on the definition and the constraints that we have. This is going to be kind of the overall pipeline, how it's going to look like. So we have some cameras from which we're going to do the reading, and we're going to do some kind of information extraction and aggregation. Based on the extracted information, we're going to take decision whether it's the incident state or not. We're going to save it into the database, and we're going to go show it to the final user using a special software that we're going to be calling Tunnel Watch. And because in the end of this pipeline, there's still a human operator that verifies that what we have detected is indeed an incident and reacts or not. So I'm going to kind of zoom in into the data, like information extraction part, and into the incident decision engine. And this diagram we're going to be reading actually from the right to the left, like from understanding what kind of incidents do we want to detect, we will understand what kind of data science building blocks do we need. So first of all, you see that the instance that we have, they're concerning special type of the agents, vehicles, pedestrian, objects. So the first thing that we need to do, we need to detect them. Hence, we have the object detection. Right? And for the object and pedestrian, we are more or less covered. But then we have the vehicle behavior. We have the stopped vehicle, we have the wrong way, and we have the slow. So all of this behavior is based on the speed. Okay? So what we want to have is the speed estimation. How do we estimate the speed though? Like we have only the context camera and only 1 per 1 zone in the tunnel, right? So in order to actually do the speed estimation, we'll need some sort of the localization. We'll need to understand where is the vehicle with respect to the tunnel. And then we'll be able to understand how fast it changes the position, hence the speed. So then you see the blocks of the localization and the tracking, which connects the object detector and the speed estimation. And then for the localization, we're going to be needing the road segmentation. Now that we understood the blocks that we're going to need, I'm going to talk about each block separately, and then we're going to combine them together into one solution. So I didn't only speak about the smoke detection, it's kind of a separate type of the incident, not connected with the other ones. We're going to deal with it separately. So, object detection. So again, we're talking about the real-time object detection, hence we opted for the one-stage detector. So it was deployed in the end of 2018, and at that time we have selected the YOLO v3. So for those who, yes, they participated in the workshop with Adela, it's pretty much the same pipeline of the training, just with the previous iteration of the architecture. You see some examples of the object detected. So the vehicles are in red, the human is in green, and then you see the, I'm going to call them obstacle objects, as the traffic cone and the warning triangle are in yellow. The next one is the vehicle tracking. Again, one of the biggest constraints is it has to be in real time and under reasonable computational power and the memory. So if you can do it simpler, it's better, believe me. And here we are using so-called tracking by detection, which means we're detecting the agents and we're detecting their location in the frame, so in the image, as the bounding boxes. Right? Like, and you see like they're in the violet and in the white. And then we need to understand from one frame to another, is it actually the same vehicle or is it another one? So we do some sort of the matching between of the frames. And this idea of the tracking is called tracking by detection. So very straightforward idea. You do it by understanding whether the boxes overlap, right? If they overlap a lot, it's probably the same object. This task has enough of the challenges, right? What can go wrong? A lot of things. So first of all, a transfer of the IDs. Like you thought it's like this car, like with a specific ID, and it was transferred to another car. Particularly why? Because of the density of the traffic. So maybe the bounding box overlap, but actually it's different vehicles. Because of the high-speed motion relative to the frame, if the bounding box is small, but then like you detect the next bounding box of the same object, which is like going to be now a bit further, so the boxes don't overlap anymore. The box is too small, and then it moved far away, right? Then you're just assigning a new ID, and you shouldn't. And finally, I think the biggest challenge that we have is the occlusion. The problem with the tunnel that the angle of the view is quite specific and you cannot put the camera higher because there is no space, right? There is the roof of the tunnel. It means that the large vehicles are going to be occluding the small ones. And ideally you have to take into account. But for now we're not going to be talking about this. And this is the idea of the tracking. I don't really think that you can see well the IDs on the cars, but they stay the same. So you just have to trust me on this one. Okay, this is probably technically the most challenging part of the presentation, so just stick with me a little bit. So this is about the speed estimation. And besides that, for the speed estimation, we need to understand where the object is with respect to the tunnel itself, particularly with respect to the road. So what I'm going to need, I'm going to understand what are the different parts of the road. For this, I'm going to be using the semantic segmentation. Then I'm going to be using the transformation of the road to bring it to the bird's eye view in order to escape the distortion that the camera gave to me. And finally, I'm going to be understanding the location of the vehicle with respect to the dashes in the tunnel, because I know the size of the dashes in the tunnel, and thus I can understand how fast was the vehicle moving. But we're going to mostly touch here the lane segmentation part. And you see here the output of the segmentation model that is overlapped with the original image, and in different colors you have different parts of the road. So the main lanes, the sidewalk, the emergency, and then in cyan you have the parking part. So every time that the instance is triggered, actually we tell to the operator exactly, not only where it happened with respect to the tunnel, like camera number 127, but also where exactly, like left lane, right lane, parking zone, etc., etc. Now the localization and the speed estimation, so I promise it's going to be a little bit more difficult. You see on the right, the image rectification. It's achieved using the homography, which we have gotten particularly from the road segmentation. So from understanding how exactly the road curves or changes the shape, we're able kind of to bring the road back to this nice rectangular shape. And then here we can detect the dashes. So hence I now understand the distance. This is kind of where all the building blocks. Now we're going to assemble them together and saying, okay, now I have the object detection, I have the lane segmentation, I have the localization. I'm actually going to try to understand how to say, okay, I have a stopped vehicle or have a runway vehicle. Stopped vehicle is probably the simplest one, right? So as we said, it's all going to be based on the speed for the vehicles. And using the speed estimation, I'm just going to smooth it over the time. And I'm going to say, okay, if my average speed is in a certain range, then it means that the vehicle is stopped. Then you're going to ask me a logical question. But where do you put speed in the range? If the vehicle is stopped, it's just less than a specific speed. Well, the speed is directional, right? So it can be negative. And I'm going to be using it for the runway vehicles. So actually, yeah, like it should be limit from the up and from the down. These are some examples of the stopped vehicles in the tunnel. They're going to be highlighted in red once the system reacts. Now the runway vehicle, so similar idea. I'm taking the momentary speed measurement, I'm averaging over time, so this helps me to decrease the measurement error. And I'm saying that if it's lower than specific upper bound, that means that the vehicle is going the wrong way. Just my upper bound is around 0. So wrong vehicle here is going to be in sign. This is like the actual incident, like they were actually filmed in the tunnel. By the way, as you can see, the quality of the video is not that high, which like brings challenges for the object detector, but we're going to talk about it a little bit later. Slow vehicle, again, the same group. So slow vehicle, like there's an actual definition of what is a slow vehicle. This is the one that has the speed below 30 kilometers per hour. And actually, like using this procedure of localization and localization using segmentation, calibration, and the dashes, we can estimate pretty well the speed. It's within like 1-2 kilometers per hour error rate. So this works pretty nicely. Naturally, the slow vehicle is often connected with other incidents. So like when the vehicle stops, before this, it becomes slow, and then it stops. Vice versa, if it was stops and it starts to go, first it stopped, and then it's slow, and then it's normal. So you see in orange here when it's slow. Finally, the congestion, so the traffic jam. So this is the example of the aggregated behavior. Before, we were characterizing every entity separately. Now I have to characterize like the group of the entities that I have in order to say whether I have congestion or not. So we give a specific definition. We say that it's going to be congestion if the group of vehicles are in the state of slow, stopped, or runway. And it looks like this. And using the localization, we also will be able to say not just congestion, we'll be able to say the congestion on the right lane. right? Because it's possible that there's a partial congestion, which is different for the operators, whether the tunnel is completely blocked or it's blocked on one side for some reason. Finally, human and small object detection. So from the decision engine point of view, it's not super challenging. Basically, you just detect a human and an object. However, from the detection point of view itself, it is pretty challenging. First, because of the varying appearance of the human and of the object. I can tell you like a couple of funny stories about this. For example, for the last tunnel that we're working on, we've been using some live simulation data, like not synthetic data, but like a situation when the tunnel is closed and then we actually simulate the incidents. So the vehicle goes there and it stops on purpose or goes wrong way on purpose, or pedestrian walk there. And pedestrian, when they work, they are maintenance workers, what do they wear? They wear like special vests. They're usually red or yellow. And what happens when you train with a lot of data like this? That's correct. So your model starts to produce false positives when it thinks that it has a red shape, for example, that looks a little bit like a human, because it has been seen a lot of humans in the red vests. Okay, so this is pretty challenging because of the different appearance of the object and the human, and of the large distance that we cover. So in this project, we have been covering the distance up to 120 meters from the camera. So kind of solution to doing it properly from our side was to have an object detector that's like with a quite wide net, in the sense of like, on the first stage, I want to have everything that looks like a human or an object to make sure they don't miss anything. And then I'm going to filter out something based on the behavior. So a good example with the human. If I detect an entity, which is a human, but it moves with the speed of the 70 kilometers per hour. So probably it's not a human, or like at least not a pedestrian. Particularly this might happen for the motorbikes, and sometimes it does. Now finally for the smoke detection, which I said which is a little bit aside in this group, because it relies on the completely different mechanisms. So we're going to solve it with the CNN, but with the particular kind of the input. We're going to be feeding the gradient from the red channel of the image, which has a certain pattern when the smoke appears. And to achieve higher accuracy, we're going to be smoothing over the time. And this is the example of the smoke being detected. You might ask me, like, why the smoke and not the fire? There are a couple of different reasons. First of all, it's the smoke that kills and not the fire. Also, smoke usually, it comes together with the fire, so the smoke detection is often enough. Plus, how to say, like in order to get the data to train the model on, to simulate the smoke is much safer, right? So we can simulate the fire, but it's not going to be an actual fire. It's going to be some sort of the proxy, right? So for the smoke, we can get a much more reliable results. That's why smoke. Then I'm going to conclude with some future work that we're planning to do. Okay, so just to put the final line. So Tunnel Watch is a Cyclope.ai product that was proposed to solve the traffic incident detection problem inside the tunnels. It performs different tasks, such as scene understanding, object detection, scene classification, and incident detection, using the deep learning methods and specific type of the decision engine. So the experiments that we have done on the collected data set, and then by actually running this solution already for a couple of years has demonstrated the usefulness of the proposed solution. What we would want to do in the future, so we want to improve system individual components for different tasks, right? We would like to incorporate additional knowledge and information from the real-world scenarios. Plus, additionally, once we have, I would say, enough of the database, we would want to improve our decision engine to make it like fully automated. Because I don't know if you have spotted, but right now we're kind of, when it comes to the whole pipeline, there are parts that are purely machine learning, so even deep learning. And then there's some parts where you have actually rules, because we don't have a database of instances large enough to be able to build an appropriate machine learning model that's going to handle it. So in the future, potentially, we should be able to go like from the formula that you have here, right, to machine learning model that's going to tell you this is a congestion. And finally, the anomaly detection component for the rare events detection. So right now we have a PhD student that's going to be working particularly on this. So not just to say detect an incident, but just detect a situation that is different from what you normally should be observing in the tunnel. So if something abnormal is happening, it's a signal for operator to have a look and to assess from the human point of view if what's happening is okay or not okay situation. And finally, so because you were sticking with me for so long, a funny GIF for you. Okay, this is we can probably say that at least we saved one cat. So this is a cat that has been detected by our system. I have only here recorded a beginning of the incident. This is the recording from the incident system, right? And after this, 2 operators were sent to rescue it. And it was rescued. So thanks so much, guys, and thanks to the Codex organizers for having us.